Ultimately, in this chapter, we're going to learn how to prove trigonometric identities. But that means we need to have an understanding of what an identity is first. And then we need some basic skills about how to change one trigonometric expression into another. To start with, I'm going to go over the trigonometric identities that we already know. To start with, we have the reciprocal identities. These should be pretty comfortable and familiar by now. The cosecant is 1 over the sine. If x is pi over 4, then the cosecant of pi over 4 can be found by taking the sine of pi over 4 and then finding its reciprocal. If cosecant is 1 over sine, then sine is 1 over cosecant, just by using a little bit of algebra. We don't actually really need this column because each one of these is the reciprocal of the ones in this column. So cosecant is 1 over sine, secant is 1 over cosine, cotangent is 1 over tangent. And then also remember that the tangent of an angle is the ratio of the sine of that angle with the cosine of that angle. Tan equals sine over cosine. Then we have the Pythagorean identities. Sine squared plus cosine squared equals 1. Dividing both sides of this equation by cosine, we get sine over cosine, which is tangent, cosine over cosine, which is 1, and 1 over cosine, which is secant. So another version of this formula, or this equation, is tangent squared plus 1 equals secant squared. If instead I divide both sides of this equation by sine squared, then I get sine over sine, which is 1, cosine over sine, which is cotangent, and 1 over sine, which is cosecant. So another different version of this equation is 1 plus cotangent squared equals cosecant squared. I don't have these memorized. I literally write this down each time and divide as I need. Then we also have something called even and odd functions. Sine is an odd function and tangent is an odd function, but cosine is an even function. By way of a quick reminder, what that means is instead of sine of x, instead of plugging in pi over 4, if you plug in negative pi over 4, you'll get the same answer as if you plugged in positive pi over 4, but make your answer negative. With the cosine, if you plug in negative pi over 4, you'll get the same answer as you do if you plug in positive pi over 4. No change of sign. Graphically speaking, very quickly, if you look at sine and cosine, you'll see that cosine has a nice reflection around the y-axis. If you spin it this way, so that it's back on a two-dimensional plane, then you wouldn't be able to tell the difference between the original graph and the spun graph. With an odd function, that symmetry is along this line here. That's a little trickier. Algebraically speaking, though, if you just plug in the opposite of the angle that you're interested in and you determine the sign of the answer, then that's the easy way to figure out whether the function you're working with is an even or an odd function. So far we have the reciprocal identities, the Pythagorean identities, and the odd-even identities. There's one more class of identities that we haven't actually really talked about yet. We've sort of gone over the idea, but we haven't actually called them identities. And those are the cofunction identities. The first of these is that the sine of x can be thought of as a shift of the cosine graph. And because of that, we can say that the function sine is a shift of the function cosine. Let's graph the graph of sine. Just a quick sketch here. If I now graph cosine x, I get the same graph, essentially. Starting that one over. It's actually quite hard to do this so that all of the pieces come through at the right place. Now I'm going to take my sine graph and go over it so that I can see where the cosine graph would be if I just shifted it over. And if I look at that white highlighted graph, I can think of that as a cosine graph that's been shifted to the right pi over 2 units. And that's exactly what I have here. This is the sine graph, but this part of it indicates that it can also be thought of as a cosine graph shifted over. Another one of these cofunction identities is that the cosine of x can be thought of as the sine of x plus pi over 2 for the same reasons. Here's the graph of cosine. Now let's put a sine graph in with it. Again, I'm just taking a minute to make sure all of my pieces line up because the sine goes through the x-axis at 0, goes through the x-axis where cosine is at its minimum. Sine is at its maximum where cosine is at 0, and so on. So now that those are all lined up, I'm going to take the cosine graph and see if I can find a sine graph in it. I could start over here and go like this, or equally, I could start back here. And since that's closer to the origin, that's what I'm going to do. So there's a sine graph, and I can write that sine, that curve, as the sine of x plus pi over 2, because it's been shifted to the left. Now, it is true that I could start here and do a full cycle of sine here, and that would give me the sine of x minus 3 pi over 2, but that starts to get a bit cumbersome. So we're going to stick close to the origin and just use this pi over 2. So instead of shifting it to the right quite a lot, I shifted it to the left just a little bit. These aren't the functions that are in your textbook. Your textbook says the sine of pi over 2 minus x, the other way around, is equal to cosine. And that's not even taking into account that the cosine is equal to sine of x plus pi over 2. There's a positive in there. So let's see if we can change this one around so it matches what's in your textbook. I'll start by just rewriting the identity. The sine of x is equal to the cosine of x minus pi over 2. Now, cosine is an even function, and that means I can either take the cosine of a positive x or the cosine of a negative x, as long as the x is the same value, and I'll get the same answer. So let's rewrite this right-hand side here as the cosine of negative x minus pi over 2. When I distribute that negative, I get minus x plus pi over 2. And if I change the order those are written in, I get positive pi over 2 minus x. So the sine, because the sine is equal to the cosine of x minus pi over 2, the sine is equal to the cosine of x minus pi over 2. It's also equal to this, because I did a little algebra. And then I did a little more algebra, and so I'm shown that it's actually also equal to this. So I started with the sine of x is equal to something that I was able to show, graphically speaking. And that means that the sine of x is equal to this, and is equal to this, and is equal to this. So that means the sine of x is equal to the cosine of pi over 2 minus x. So I can write this either as the cosine of x minus pi over 2, or as the cosine of pi over 2 minus x. Essentially, what I've done here is a very small proof. I haven't written it formally. I don't have any statement of what I want to prove or any sort of conclusion. But what I've done is taken one side of my equation that I knew for sure was true and manipulated that right-hand side until it got into a different form, the form that I was actually looking for. So don't worry too much about that right now, but that's kind of a heads up about the kind of things we're going to be doing when we start talking about how to prove identities a little bit later in this chapter. Now, unfortunately, we don't have the tools just yet to show that the second one is true, that the cosine of x is equal to the sine, let me change that, is equal to the sine of pi over 2 minus x. It is. It's another way to write that, pi over 2 minus x. And that gives us these two identities in the same form that they are in your textbook. Scooch this one over here. So now those two look like they do in your textbook. I'll write the other ones out so we have a complete set. We have that the sine is equal to the cosine if you shift it over. The cosine is equal to the sine if you shift it over. Tangent and the cotangent and the tangent, the secant and cosecant, cosecant and secant. And the shift is the same. Start with pi over 2, subtract x. These are called the co-function identities because they deal with the co-functions. The sine has a co-function of cosine. Tangent and cotangent and secant and cosecant are co-functions. So why have we gone to all the trouble to list all of these? Well, this is a handy identity to know about. And the fact that we've got these all in the same form, pi over 2 minus x, means you don't really need to memorize them. If you remember this one, or write it on a note card, all of the other ones follow suit. They're all the same shift because of the algebra or trigonometry or whatever it is we did to get them in that form. This first one is the only one that I've sort of demonstrated for you. We'll demonstrate some of these other ones perhaps if we have time as we go through the course. But the idea is that I can change the sign. We know that the sine of x is equal to the cosine of x minus pi over 2 just because of the graphical representation of the two functions. I've been able to prove that the sine of x is equal to the cosine of pi over 2 minus x by doing some algebra on the right-hand side. So now we have the cofunction identities in addition to our reciprocal identities, our Pythagorean identities, and our odd and even functions. These are also identities. What makes them identities is that the left-hand side and the right-hand side are equal for any value of x. I think it might be worth talking a little bit about the difference between an equation and an identity. So I'll do that on the next screen. So what is an identity? Well, both of these are equations, right? They have equal signs in them, and they have stuff on one side and stuff on the other side, and the claim is that those two things are equal. In the case of the first one here, I can solve this equation by subtracting 3 from both sides, and I get that x is equal to 2. So that's the answer to this question, if you will, the solution to this equation, but it's the only solution. The only thing x can be here is 2. This is a true statement only if x is 2. On the other hand, this is also an equation. Can I solve it? Let's try subtracting x from both sides. I get x equals 2x minus 1x is x. That means x can be anything because the solution to this equation is that some number equals that same number. Well, that's always true. And it doesn't matter what x is. I haven't tried plugging a number in to see if it's true for that particular number. I've discovered that this statement up here is true for every value of x. No matter what I plug in here, I'm going to end up with a solution that looks like this. X is equal to x is true for any value of x. That's what makes it an identity. Let's try solving this equation a different way. If I have x plus x equals 2x, and I simplify the left-hand side and I get 2x equals 2x, well, we've kind of got another duh moment, don't we? X equals x. So no matter what I do, I end up with this statement at the end, which tells me that not only is the original statement true, but that it's true for every value you might plug in, every possible value of x. That's what makes it an identity. This one's not an identity because it's only true for one value. If I had, for example, x squared plus 3x, let's go with x squared plus 6x plus 9 equals 49, then I could start by trying to subtract 9 from both sides, but I'd end up with an x and an x squared, so that's not going to work for me. I don't know if you remember this from algebra, but if I factor this, I get x plus 3 quantity squared. The right-hand side is 7 squared. If I take the square root of both sides, I get, now I should be a plus or a minus, but I'm just trying to make a point here, so I'm going to go with the positive. If I subtract 3 from both sides, I get x equals 4. One solution. So this equation here only has one solution, so it is not an identity. This one is not an identity. This one is, because no matter how I try to solve it, I end up with a statement x equals x. X is always going to be equal to x. So any number x will do. Okay, so what we've done so far in this video is we've reviewed all of the identities that we already know. I've added a few by actually going over what a cofunction identity is. And I've described what an identity is in comparison to just any old equation. So now what we're going to be doing with this is simplifying a trigonometric expression. And to a certain extent, we've already done some of this. For example, if I asked you to simplify cosine theta over sine theta, you'd be able to say, well, that's just tangent theta. Actually, it's not. It's cotangent theta. The answer here is cotangent theta. You have simplified this expression. The idea with trigonometric expressions, or simplifying trigonometric expressions, is going to be to try to get them down to as few expressions as possible. This involves both a cosine and a sine, but this one involves only one trigonometric ratio, the cotangent. So we're going to be trying to get them down to one ratio if possible, but in any case, as few as possible. This was a very simple one. Let's take a look at another one. Simplify the ratio, the tangent of x over the secant of x. Well, I know that the tangent of x can be written as the sine of x over the cosine of x. So I've actually had to make this one more complicated before I can make it less complicated. The secant of x can be thought of as 1 over the cosine of x. Therefore, the tangent over the secant is the sine over the cosine over 1 over the cosine. Well, that's sine over cosine divided by 1 over cosine is the same as cosine over 1. And now look what happens. I'm left with just the sine of x. Now, I haven't done that one very neatly. I've kind of taken some shortcuts here, but I've done that intentionally to try to show you how I've taken each part of this expression up here and rewritten it so that when I put them back together in a ratio in its own right, I can simplify that ratio. Okay, let's try another one. This one's another fraction, but it's not as straightforward a fraction, not quite as straightforward a ratio as the other two that I've done so far. So I'm going to need to find a way to simplify things in general. And one strategy is to get everything in terms of sine and cosine. I've got a sine here and a cosine here, but let's try changing the secant into something involving either a sine or a cosine or some combination. The sine of t over, and I'll just write minus the cosine of t for right now. The secant of t is 1 over cosine. So I can change that from secant to 1 over cosine. This expression here is equivalent to this expression here. So I've used an identity to change the way this expression looks into this one. Now, I'm going to try to add these two fractions together, so I need a common denominator. Let's make this times cosine over cosine. That means that my common denominator is now cosine, so I have sine over 1 over cosine minus cosine times cosine over cosine. But because I have a common denominator, I can now combine that. I still have my sine in the numerator, and I'm going to have over cosine. And in the numerator of my denominator, I'm going to have 1 minus cosine squared. Well, I have another identity that I know for 1 minus cosine squared. This is kind of a transitional lesson. Some of you might recognize that 1 minus cosine squared already, but others of you may not. So at this point, I'm still going to help you try to figure out what goes where. I know that sine squared, let's use x. Sine squared of x plus cosine squared of x equals 1. And I also know that if I subtract cosine from both sides, using perfectly legitimate legal algebraic moves, you can come up with a different expression. I can write sine squared as 1 minus cosine squared, which means I can write 1 minus cosine squared as sine squared. So I'm going to write this now as the sine of t over, there's my cosine of t down there, and 1 minus cosine of t is sine squared t. So this is my big fraction bar here. If I put sine of t over 1, then I have a fraction over a fraction. So a fraction divided by a fraction is a fraction times a reciprocal, so I'm going to rewrite this as the sine of t over 1, not divided by sine squared over cosine, but times cosine divided by sine squared. Now I can simplify. Down here, I have sine times sine. That's what this means. Sine squared means the sine of t all squared. So I have 2 copies of the sine of t, and I have 1 copy here. So I'm going to cancel that with one of those. And that leaves me with cosine over sine. And if I want my expression to be in terms of sines and cosine, I'm done. But if I want to reduce it to a single trigonometric ratio, then I can do one more thing here. Because I know another identity, and I have to recognize it, cosine over sine is cotangent. So I have taken, where did I start? this expression here and simplified it to simply cotangent. Now, it's taken me a lot of steps to do that. Remember our first one here, we just said, oh, I recognize that. I can simplify it simply by recognizing that as an identity I already know. One step. In the second one we did, we had to rethink what tangent and secant were. Another way to think of tangent is this, another way to think of secant is that. So this ratio of two trigonometric ratios becomes this ratio. It's a very complex ratio. But then we just did some algebra. We inverted this bottom fraction, simplified, canceled, and we ended up with our answer. So this one was, let's see, it looks like basically one, you could count that as two steps, I suppose. Inverting and multiplying is a third step, and simplifying was a fourth step. So this one only took us one step. This one took us four. This one took us, let's see, 1, 2, 3, 4, 5, 6, 7, the canceling, 8, 9. That one took us 9 steps. Some of them will take more, some of them will take fewer. Let's try another one on the next screen. My goal with this one is to show you that you're not always going to start with a fraction either. Now, these all have negative x's in them, so I'm going to use the even and odd functions to simplify this. Notice that I have an expression here times an expression here plus a third expression here. Now, I know that the cosine of negative x is just the cosine of x. That's because it's an even function. The sine of negative x, well, the sine of x is an odd function, so that's going to be negative the sine of x. Cotangent's a little bit trickier, but let's do a little scratch work over here. We know that the cotangent of x is equal to the cosine of x over the sine of x. If I take this x and make it negative, let's just use a pink pen here. I'll make that a negative x, and that means my input for all of these is negative. So I now have that the cotangent of negative x is equal to the cosine of negative x, which I know to be the cosine of x, over the sine of negative x, which I know to be negative the sine of x. So I end up with negative the cosine of x over the sine of x, or negative cotangent of x. I started with cotangent of negative x. Actually, I'll use this line here. Cotangent of negative x is equal to negative the cotangent of x. So I can replace the cotangent of negative x with negative the cotangent of x. Now that was the first step. It involved 3 different even-odd identities, but that was just the first step. The next step is to take each one of these expressions and, as much as possible, reduce them to only sines and cosines. Well, cosine and sine are already sines and cosines, but the cotangent, remember that term is negative, that factor is negative, so I have negative the cotangent, which can be thought of as negative cosine of x over sine of x. Well, now I have a fraction, so let's go ahead and make all of these fractions. I'll change that to a minus. That first product of 2 fractions, actually, I can combine. I'm going to end up with negative cosine squared of x over sine times 1, which is just sine, minus the sine of x over 1. And that, I think I will change. Now I'm going for a common denominator. I have sine in the denominator of the other fraction, so I want sine in the denominator of this fraction. And then I can rewrite this as negative cosine squared of x minus sine squared of x all over sine of x. Now, if this was cosine squared plus sine squared, or sine squared plus cosine squared, I'd know that was 1. And in fact, since both of these are negative, I can factor that negative out. And I get cosine squared plus sine squared. Let's move these up a little bit. And for my last step, recognize that that numerator is negative 1. I'll bring the negative out front and rewrite it as 1 over sine. Now, I said last step. It might be your last step if your instructions were to get the expression in terms of sines and cosines. But if you really want to simplify it all the way, you'll have a single trigonometric ratio, no fractions. So that makes this one negative cosecant of x. Now, something I'd like to point out about this particular problem that we just did is that I had to use the idea that the cotangent of negative x was negative the cotangent of x. And I did that, I worked that through over here, kind of on scratch paper. It's not necessarily an obvious thing. So because I knew cosine of negative x was cosine of x, and sine of negative x was negative the sine of x, I was able just to write those down. But cotangent was less obvious. So I can either do the work over here on scratch paper, or kind of off to the side, or I can actually do this work right here and here. But if I do, I need to be careful that what I'm saying is that cotangent of negative x is equal to, and rewrite cotangent of negative x as this ratio here in the next step. And then in the next step, rewrite it again. And then finally, in the last step of that process, write it again. So that would have introduced 2 more lines in here. Each time I'm changing this factor, but leaving these factors as they are. It's a tricky balance to strike. The work that I've done here has taken each expression in its own right, as it were, and changed it one step at a time. So there's one thing that I did. In that same step, I also rewrote sine of negative x. For some reason, I've got the wrong pen color here. Sine of negative x is negative sine of x, and cosine of negative x is cosine of x. I did all of those 3 things in the same first step. If I had done this work as a part of that, then I would have had 2 more lines in here. These wouldn't have changed from one line to the next, but this one would have changed a couple of times. Then in the next step, I changed cotangent into cosine over sine. The other 2, I just put over 1. In the next again step, I got my common denominator and multiplied these 2 to get a single fraction here. And then I also, in the same step, got a common denominator and applied what I needed to apply to get that common denominator to that factor, to that term. In the next step, I combined these 2 now fractions with a common denominator into a single fraction. In the next one, I just factored out the negative. And in the next one, I recognized that cosine squared plus sine squared was 1. And in the last step, I changed sine, 1 over sine, to cosecant. So each step is a copy of the step above it with a change or 2 or 3. And what makes it easy to read then is that I can follow from one step to the next pretty much in a straight vertical line to see that this expression equals this expression equals this equals, okay, here I had to do a little multiplication, but it's these 2 factors right here getting simplified and combined into 1. And then these into this one. And this is just another way to write this, and so on. If you tend to be pretty neat and organized, this will all make perfectly good sense to you. But if you tend to be a bit more relaxed in how you record things and write them down, then you're kind of going to have to get more organized. Part of the point of this kind of work is that you are communicating to another mathematician who may not be in the same room. Heck, they may be across the world. You're trying to communicate your process for getting from point A to point B. And the process is as important, if not more important, than the result. So figuring out how to write things in a neat, organized way is absolutely critical to success in this unit. All right, I think I'm going to let it go for this video. There is an additional strategy that's addressed in your textbook, simplifying by combining fractions. We kind of addressed that here. We didn't start out with fractions in our original expression. We ended up with fractions, and so we had to add those two fractions together to get our whole expression into a single fraction. And that's essentially what you're going to do here. The one in the textbook is sine over cosine plus cosine over 1 plus sine. Now, to get a common denominator there, you need to multiply the first fraction by 1 plus cosine over 1 plus cosine, and the second fraction by cosine over cosine. So it can get a little messy, but the steps are pretty much the same as what we did here. Find yourself with two fractions. Make sure you have multiply by what you need to multiply to make sure you have a common denominator. Combine the two fractions. That's pretty much it. The best way to get good at these is just to do a lot of them. So my suggestion is that you do as many of the textbook problems as you can. I've assigned a few, most instructors will do that, as a way of saying this is kind of the bare minimum of what you need to do to get some practice doing problems like this. If your homework ends up being collected, then you've done the minimum that you need to do to get the grade. But the point for me is not to get the grade. The point for me is to get the practice. Because what really matters is whether you're going to do well on the exam. And you'll do well on the exam if you've had a lot of exposure to a lot of different kinds of problems, all of which are asking you to do the same thing, simplifying a trigonometric expression. Once we've learned how to simplify expressions, we're going to use that skill in a deeper skill, and that's what's coming next.